Okay, everybody, we're going to try using a software that I found and just see how it works out. Because of class time, last time seemed like we bounced around a lot and really didn't get at what logarithms were and how to use them. So we're going to do a little brief review and then jump back into logarithms, and hopefully this will help you. So first we'll review the inverse function. And remember that the inverse function is if you have some function, f of x is equal to x squared. When we take the inverse, it looks like this. First we change f of x to a y, and then we replace x and y with each other, so this becomes x equals y squared. And then we solve for y, so y equals or plus or minus square root of x, and then we replace y with what's now the inverse function, so f to the negative 1 of x is equal to plus or minus square root of x. And then we discussed the exponential function. And remember, the exponential function is anything that looks like this: y equals b to the x. And we learned a couple of rules. If b is greater than 1, your graph will look something like this. So b is greater than 1. And remember that we know that it runs through these 2 points, 0, 1, and 1, b. And then for b is less than 1, we know it looks something like this. And again, we know it runs through 0, 1, and 1b. And this leads us into our discussion on logarithms. And a logarithm is basically just the inverse of an exponential function. There are 3 basic types of logarithms that we're going to concern ourselves with. And the first is just when we have a log that has base b times x is equal to y. Not times x, log base b of x is equal to y. The next one is the natural log, which is log base e of x is equal to y. And then the common log, log base 10 of x is equal to y. Now all of these are really just the exact same thing. In fact, if anything, they're all really built around this guy. They all follow the exact same rules. The reason we happen to have a log base e, also known as natural log, often to just say this is the exact same way of saying natural log, and log base 10 is because log base e and log base 10 give us 2 good circumstances that happen a lot. And so we want to have these as kind of stuff that we can lean on constantly. However, this also adds a level of complexity, because in dealing with logs, now we need to, we might have 3 different types of bases pop up, or even more if we have 2 different kinds of log base b's. We might have log base 2, log base 10, a log base 3, log base e, and so we have to be able to also switch between log bases. And we also need to know how to use these and how to solve them. So that's really where the meat of this lesson, that's where we get into the meat of this lesson. So first we really need to ask ourselves, what is a logarithm? And really all a logarithm is just a way to solve an exponential function. So we saw that we had those things, the exponential function where y is equal to b to the x. And we know that, from what I said in class, and from what I said earlier, that logarithm is the inverse of the exponential function. So if we took the inverse of this, it would be x is equal to b to the y. And so depending on the definition you want to use, the most mathematical definition is that the logarithm is the inverse of an exponential function, and such that x equals b to the y. So if that all just kind of seems like a lot of math speak that's hard to get your brain around, and you really don't know why I'm even saying that, that's okay, because honestly, I haven't given you a lot of background, and you probably you haven't experienced a situation in which you would want to solve for an exponent. But that's what algebra is all about. We're going to show you how to solve these things. When it comes to time that you ever have to use it, you'll know what to do as far as solving a logarithm or employing it even. And so what we're going to do is then we'll walk through the properties of logarithms, and then we're going to talk to you how to change the base of a logarithm. And that's really going to be what you need to solve the questions in 5.4 and kind of get you started. And I'll send along the homework I expect to do for 5.4. And this will hopefully give you guys a head start so that it's not so crazy whenever I assign homework this coming Thursday. So the first thing we're going to dive into is the properties of logarithms. You'll have to excuse the fact that every time my pen touches the screen there's going to be a loud clink, and there's going to be a lot of them because there's a lot of properties. Well, there's 3, and but it requires a little bit of writing from me, and that's going to make a lot of clicking noises. So if, hopefully that's not too bad for you, and we'll just kind of chug along here. So the first thing is the product property. We have log base b of mn. This is all coming from the purple box on page 467, by the way, is equal to log base b of m plus log base b of n. So what that means is if I have some log where these are being multiplied, remember the log is the function being taken of whatever it is, so I'm taking the log of m times n, and so I can break that out into log m plus log n. So if we let's use a made example, and let's just see here. So we have log base 2 of 5x. So that's the same as log base 2 of 5 times x is equal to log base 2 of 5 plus log base 2 of x. So that's as simple as the properties of, and that's as simple as the product property goes. Next we have the quotient property. It's very much like the product property. So if we have a log base b of m divided by n, then the same way that if we were multiplying m and n, we could add them together. Well, now if we're dividing m by n, then we can subtract. So whatever's in the denominator becomes the subtractor, the thing you're subtracting. So that's not a real term, by the way. Don't ever use that and think you're going to be, people are going to think you're a smart mathematician. So just ignore that part. But we get log base b of m minus log base b of n. So again, if we use our previous example, kind of modify a little bit. If we have log base 2 of 5 divided by x, that's the same as log base 2 of 5 minus log base 2 of x. Okay, and lastly we have the power property. And this is actually the easiest one that we do. So we have log, I'm going to go back to printing here in a second, log base b of m to the p power, that's the same as p times log base b of m. So if we use another example here, if we had log base 2 of let's do something kind of, let's just call it log base 2 of x to the 5th. That's the same as 5 log base 2 of x. And this leads us into change of base formula, because if we have two different bases, we have two different logarithms that we're trying to use in one formula, and they each have their own base, we're going to need a way to change the base of one of them to match the other. So as a kind of made up example here, if we had natural log of x plus log base 3 of 5, how do we accomplish this? Well, we're going to have a similar base. Just like other functions that are complex like this, there's a lot of rules surrounding this, so we can't just start making up whatever we want to do. We have to be able to follow a specific rule and then arrive at the conclusion. In this case, we have to have like bases before we can begin to mess with these logarithms. So the first is the base E change of base formula. And what this does is if you have a natural log of some number, if you divide that number by the natural log of the base you're trying to achieve, then you'll get a log base, whatever this new base you're trying to achieve is, m. So to put this in writing, if we had log base b is equal, log base b of m is equal to natural log, which again is log base e. I'm going to write it both ways. Natural log of m divided by natural log of b. So what we're saying is if we want to achieve log base b, what we need to do is divide by the natural log of b. So if I had some natural log, which remember that means log base e is the same as natural log. So if I have some natural log, erase that right fast here. So if I had some natural log, and let's just call it 5x. That's been our favorite term here. And I wanted to change this so that I got a base of 3. Remember, right now my base is e, and I want to get to base of 3. So my base that I'm after. So to do that, I would have natural log of 5x divided by, you guessed it, natural log of 3. And what this would produce is log base 3 of 5x. Hopefully that makes sense, and we'll be using that in our homework. So I'll give you a couple of examples in the homework, and that'll give you something to work through that kind of help, hopefully make a little more sense. So next up is the base 10 formula. So if I was trying to achieve some log base whatever b of some number m, then I would just divide by the log base 10 of the base I'm trying to achieve. So to put this in writing again, if we want to achieve log base whatever b, some number 2, 3, 8, 12, 100 of some number m, and all we have is a log base 10 of m, often also called log m. So this is a little term. If you ever see someone use just log of anything, it's implied that they mean log base 10, and that's why they call it the common log. It's like, oh, you're using log, and if with no base number, then it's so common, I suppose, that you're using log base 10. For now, we're going to put log base 10. Even though in your book on page 469 it does not show base 10, that's what's implied by just writing log m. Log base, if I can write it here, 10 of m, divided by log base 10 of b, the base you're trying to achieve. And so that results in log base b of m. So if we had log base 10 of 5x, we wanted to get a base of 3. Remember, our base we're going to shoot for is 3. I apologize for the writing, but it's hard to do on the screen here. And so what we would do is we would say log base 10 of 5x divided by log base 10 of 3 is equal to log base 3 of 5x. So that's very much like the natural log, and you're going to see it's the exact same for what they call the arbitrary base a. I hope you're seeing a pattern here because it's basically going to be the exact same thing, only for just any base now. We're just going to say whatever base you're starting off with, how do you get to base b? So if I had some arbitrary base a, it could be 20 or 100, how do I get it to a different base? Like 3. Well, we would take whatever it is that we have our logarithm that we start off with, and we would divide it by the logarithm of the same base of the base we're trying to achieve, and we'd end up with the logarithm of what we originally had with the new base. So, to put that in writing again, if we want to achieve some log base b of m, and we start off with log base a of m, then we would divide it by log base a of b. So I hope you're seeing a pattern. Basically, whatever we're trying to achieve, we take the log of the same base we take the log of the base we're trying to achieve of the same base that we had before, and we end up with the base that we're trying to achieve of the original number or term. So, I mean, really, if you really think about it, this arbitrary base a is the exact same rule that we applied for the base c and base 10 change of base formulas. But this is just a more generalized way of looking at it. So really, it's the same thing 3 times. They just give them 3 different names. So if you can learn it for this one, you'll basically know it for the other 2 as well. So if we had some log base 100 of 5x, we could achieve a base of 3 by dividing by log base 100 of 3. And that would yield log base 3 of 5x. So not too crazy, right? It's the same thing we did for natural log and for common log. Okay, so I'm not going to do an extensive amount of example problems. I'm actually going to save that for class on Thursday and kind of run through what we talked about quickly for those of you who weren't able to watch the video, and then assign the problems, and we'll do a few examples in class. But I figure I can at least do one for you guys right here, and this will hopefully give you an idea of what to do for the homework when I send that out. And again, I'm going to send out the homework with this so that you guys can get a little head start on it. I would recommend just doing some of the odd problems along with the evens, and that'll give you a better idea what's going on. If that sounds like too much work, it's going to be a hard next week because you're going to have to combine this homework with the next, and it could result in a long homework session for you. So, I apologize I can't be able to do all the examples here. If I'm feeling really generous, tomorrow I might try to accomplish some more and give you guys a better idea of what's going on and what to expect. But let's dive into at least one example problem for you, and hopefully this gives you a little bit of an idea of how to do these. So the first example I'll do is to show how to use the product property. So just using number 25 from your book of lesson 5.4, if we have log base 2 of 7 plus log base 2 of 6, and remember we're only going to write the expression as a single term, so we don't have to solve it. We just need to write log base 2 or whatever this is. So using our product property, we know that anything added together with the same base is the same as the product. So if we had, we can change this to log base 2 of 7 times 6. It is the same as log base 2 of 42. Oh my goodness. Can't write. There we go. Log base 2, 42. And that's all they require in your book. They don't expect you to write it. Next, let's look at example number 62. If we have the natural log, remember that's log base e, of the cubed root of pq You'll just have to suffer through my writing on this because it's hard to do on this little iPad. Then we can employ one of the properties, and that's the power property. So remember that the cubed root is the same as 1/3, right? So this is the same as the natural log of pq to the 1/3. And remember, the power property says that we can move this 1/3 in front of the natural log. So this becomes 1/3 natural log of pq. And then we can go ahead and even use one more property, and we can use the addition property, or the product property, so that we can change this into 1/3 natural log p plus 1/3 natural log q. Is this simpler? I think so. If we think about if p or q happen to be a variable, then this would be the easier way to put these, because then we have a variable that stands alone and we can mess with that. So it kind of depends on what you're looking at p and q as, if they're actually coefficients or variables. But if they're variables, or if at least one of them is a variable, this is the easiest way to present it. I wouldn't ping you if you were to put on your homework this answer. This is acceptable as well. So I'm going to solve one more, and I know I only said I would do one, but in this case I think it's important to keep moving. I know I've already done two. I said I would do one. I've done two. Here comes the third one. I think this is important because I kind of misled you in the way to do change of base formula. And by that I mean I didn't give you any wrong information. But if you're looking at just what I showed you, then it may be hard to solve something like number 71. Because even though I was absolutely right, if you're chasing after a different base, then you would divide by that logarithm with the same base you are using at that moment, the logarithm of the base you're chasing after, and then you would end up with the base you're after. But another way to look at this is, if I'm trying to, if I know I want something to be equal to a natural log or a log base 10, and I don't know what that is, then I can basically use that formula in reverse. So that's a lot of words. Let's start actually talking. Let's actually work through a problem, and you'll see what I'm talking about. So if I have something like log base 7 of 60, which is number 71 of lesson 5.4, you might be like, oh, well, it's already solved for me. I'm just going to punch this bad boy into my calculator. And you reach to your calculator, and you would see there's no such thing as a log base 7. In fact, I think almost all calculators, unless they're really, really, really advanced, only have log base e, or natural log, or log base 10. And so we need to be able to write this as a log base 10 problem. So if we work kind of in reverse, we know that this is the same as log base, I'm going to use log base 10, we could have used natural log as well. I'm going to use log base 10 of 60 divided by log base 10 of 7. And so I can plug each of these into my calculator, log base 10 of 60 and log base 10 of 7, and that gives me log base 7 of 60. So we kind of worked backward. We normally chase after a certain base, but in this case the base 7 was really not useful, and we could have divided log base 7 of 60 by log base 7 of whatever base we're after, like 10. But again, how do we divide that? We can't plug it into our calculator. So we plug this into our calculator, and the log base 10 of 60 is 1.778, and the log base 10 of 7 is 0.845. So that means that the log base 7 of 60 is, we divide those by each other, so 2.104. And I shouldn't use an equal sign, I should say it's approximately, so actually. So there it is. That's how you would solve something that has a funky base on it. You would change it over to a log base 10 or natural log, and then plug that into your calculator.